Dear students, good afternoon to both of you. I am Dr. Dinesh Kumar, Principal Scientist, Division of Agronomy, IARI, New Delhi. Today is 26th February 2025, very auspicious day of Maha Shivratri. I just wish all the best to you and congratulate you on the eve of this festival. So we continue with the topic, methodological interpretation of fertilizer experiment. I just already gave you introduction to this chapter. You have already noted down references, and you also know what we are going to cover in this lecture. I started with showing you to work out the economics of crop production or crop cultivation, giving example of cauliflower or rice. So in this case, we need to work out the common cost of cultivation, and then the additional cost due to variable or due to treatment. So that way we can work out the economics. In economics, we need to work out the benefit cost ratio. So this is how we can work out the benefit cost ratio. So you see the common cost of cultivation is in the second last column, and then third last column, you can see the total cost of the treatment. When you add these two columns, column number 1, 2, 3, 4, 5, and 6, you get column 7. So this is your total cost for the individual treatment. And then we can work out the prices of the output and deduct these total cost, and you will get the profit, or you will get the net return. Net return can be obtained by total price of the output minus total cost. So finally, you get BC ratio. It is calculated from net returns, and net returns are divided by cost of cultivation. Then you get BC ratio. So I told you that here our purpose is to optimize the dose of the fertilizer. So how to optimize the dose of the fertilizer? There are different approaches. I told you about visual plant diagnosis, plant tissue test, plant chemical analysis, critical values, or soil chemical analysis. These two can be combined. So I was referring, or I was saying that by analyzing the nutrient status of the soil, we can have some idea, but we cannot give recommendation of the fertilizer based upon just soil testing. It is not enough. We do not know how much contribution of nutrients can come from soil. How would we know? By testing the soil. Whatever NPK or micronutrient content is there in the soil, we have tested it. But merely upon this information, we cannot give recommendations. And what soil scientists used to do to give recommendation under such cases, they used to have classes like low, medium, high. If it is low, response will always be there. And they say apply 100% recommended dose if you have low status of nutrient. Apply, say, 50% or 50 to 70%, 75% of the recommended dose if your nutrient status is medium. And then if it is high, no need to apply any nutrient. So this was the recommendation. But this is, again, this can be very vague. Even if it is high, how can we know that what proportion of nutrients available can be made available to the plant? So that is incomplete approach. And slowly, I'll show you what is the best way to tell the farmer or to know the exact requirement of the nutrients depending upon the soil. It is very, very location is specific, soil is specific, climate is specific, such kind of recommendations. So now see critical value or critical level. Do you know what is critical level of nutrients for deficiency and critical level of nutrients for toxicity? Any idea about this? What is critical level of nutrient?
It is the concentration of the nutrient below which the deficiency symptom generally appears.
Yeah, you are partly right, but people have defined it like this. I tell you now. It is, remember, there are two things. One is critical concentration of nutrient for deficiency, and other is for toxicity. sometimes you can get excess accumulation. So how can we decide? So people have already decided if plant accumulates so much of concentration of the nutrient in excess, at which plant starts showing symptoms of toxicity. So symptom of deficiency when your nutrients are deficient, symptom of toxicity when your nutrients are in excess. Another combination is that this critical concentration is referred with respect to plant as well as with respect to soil. So now you got 4 points, 2 variable. One is concentration, low, high, or non or low or excess. Other is soil and plant. So now you have got total 4 things. So for 4 things, it can be very simply defined. The concentration of nutrient in plant or in soil at which 90% of the maximum attainable growth or yield is possible. 90% means if your growth is growth is reduced by 10%. 10% growth is reduced at that particular level where you get 10% reduction in growth or yield of plant is called as critical level for toxicity, critical level for deficiency in soil and plant. Critical level for deficiency in soil, critical level for deficiency in plant. Is it okay? Now you reverse it. Now you continue to supply the nutrients and it becomes in excess. Then there would be excess accumulation. So accumulation or concentration of nutrient in plant at which toxicity symptoms are seen, and there is 10% reduction in the growth and yield of plant. So that particular concentration in plant or in soil is called as critical concentration for toxicity. Critical concentration for toxicity. So I hope you understand this critical concentration. It is always defined with respect to plant growth or plant yield. Either of these can be taken. You can take with respect to growth if it is in growth stage, and finally, if it is in yield stage, you can define critical concentration with respect to yield also. So this critical concentration cannot tell us how much to be applied, how much nutrient to be applied. So then what can be done? We can go for conducting pot experiment, or we can go for conducting field experiment. So field experiment is the final solution. I will tell you how it is the best way to give recommendations for nutrients. So now see, critical concentration is that level of concentration of a nutrient in the plant or in soil that is likely to result in 90% of the maximum yields. So at this level, you are getting 90% growth or 90% yield. At this level, maybe in plant or maybe in soil. Maybe low, maybe high. Low means deficiency, high means toxicity. Now you see this picture is very clearly tells you different kind of plant growth and nutrient supply responses. So you can see, friends, here on x-axis, you have the concentration of the nutrient in plant or in soil. In x-axis, there is no any quantitative value. This is very relative picture. It is showing you just relative values. So from left side to right side, if you move on x-axis, the values are increasing. Means concentration of nutrient either in soil or plant is increasing when you move from left to right. Similarly, on y-axis, the yield or growth is increasing as you go from lower side to upper side. Now, in the beginning, the nutrient supply in soil or availability in plant is very low. So here you will get acute deficiency. Now you are increasing the supply, then growth is also increasing. You increase more supply, growth will increase, but plant can have at this stage latent or hidden deficiency. It may not show symptoms, but it is deficient. So during this zone, latent or hidden deficiency, lies the critical value, lies the critical value. If you see the value at y-axis, it would be 90%. It would be 90% relative growth. Now you increase the supply from B point towards C, then you will get maximum yield zone. This is maximum yield zone. Here, somewhere in this zone lies the optimum supply of the nutrient. And then in some nutrients, you can get luxury consumption, like in potassium. However, yield is not affected. Here you can see the yield is not adversely affected. You are getting the maximum yield at this level, but it is a wasteful use of the nutrient. And then for other nutrients, potassium is never toxic. Okay, it can be accumulated in excess, but it is not considered as toxic nutrient. Toxicity is related to the micronutrients, not secondary nutrients or primary nutrients. Then initially there may be light toxicity of micronutrients, and then it can be acute toxicity. So somewhere here at this point, you see the cursor, at this point you will have 90% growth. So this will be critical concentration for toxicity. And concentration is on x-axis, maybe in soil, maybe in plant. So for toxicity, the critical concentration is very high, very high. It may be somewhere here like this. So this picture explains you very well, and you can practice making this picture. This will help you to write your answers more effectively. So practice this picture 1 or 2 times so that you can use it in your soil fertility exams or any other competitive exam. It will leave more impact on the examiner. Now you can check the critical limit in soil and plant tissues, fully developed youngest leaf. So whenever we define the critical concentration, first foremost thing is that we have to specify whether you are talking it for soil or for plant, number 1. Number 2, whether you are talking for deficiency or toxicity. Number 3, which plant part you have used. You have to mention the 4th leaf from the top, 2nd leaf from the bottom, or petiole of the leaf, and likewise, or blade of the leaf. So you need to mention which part of the plant you have used. So part is also important. And also you need to mention what was the age of the plant or stage of the plant, because critical concentration varies with the stage of the plant. And sometimes it also varies with the soil type also. So there are many variables which affect the critical concentration. It is mostly stage, type of plant, type of crop. For rice, critical symptoms or deficiency, critical level may be different from wheat or mustard. So plant type affects, plant part use, at what stage you have taken the sample, and then is it for soil or plant, likewise. So these are important things which we need to mention. So critical concentration is not for the whole life of the plant, and it is not uniform for all plants. It is not uniform for all soils. So that is why many times you will see that they mention the stage also. So for example, in soil they have given the critical concentration, and for micronutrients, you know, they can be extracted by different agents. Boron is normally extracted by hot water from the soil, but zinc, manganese, copper, and boron, they can be extracted by 2-3 different extractant, but DTPA is the most common, which extract zinc from the soil for analysis, this DTPA. So if DTPA is extractant, then critical concentration in zinc is 0.6 ppm in soil. You can remember this value, microgram per gram. Microgram per gram, you can write. You can also write milligram per kg, milligram per kg. So microgram per gram is equivalent to milligram per kg. And milligram per kg can also be written as ppm. Okay. So this unit, microgram per gram, is equivalent to milligram per kg. So for DTPA, 0.6 ppm or microgram per gram. And for manganese, 2 ppm is critical concentration. Iron, 2.4 to 4.5, copper 0.2. For boron, it is 0.5, and for molybdenum, it is ammonium oxalate, pH 3.5, it is 0.2 ppm in soil. In plant tissue, of course, here they have not specified the stage, but you can see general range of critical concentration. For zinc, it is 10 to 20. They have not defined even plant also, which plant part is used, but these are very general values of zinc, 10 to 20 ppm, for manganese 15 to 25, iron 50, it is little more, copper 2 to 5, and boron 5 to 30, and molybdenum very low, 0.03 to 0.15 ppm. Now, you can check how I am summarizing what has been told to you up to now in this table. So you can see methods for evaluation of soil fertility. Whatever we have seen, these were practically all were evaluating the status of nutrient in soil. For example, visual diagnosis. Symptom first appear on old leaves or young leaves. So it gave us indication whether a particular nutrient is deficient or not. But it never gives up idea how much to be applied. Then rapid tissue test or plant analysis. You can do two kind of tests. One is rapid tissue test that can be done. Number two, total analysis of nutrient. This is quantitative approach where you do plant analysis and then see the concentration of nutrients in different plant parts, and based upon the critical concentration of nutrients, you do interpretation whether your nutrients are sufficient or insufficient in the plant. There are three different approaches by which we can interpret this critical concentration. Is one. Other is nutrient ratios by DRIS. I will teach you this in soil fertility course, this DRIS. And then chlorophyll meters can be indirectly tell us status of nitrogen in some crops. So two are important: critical concentration of nutrient and nutrient ratios. Now, soil testing, the third option for evaluation of fertility is soil testing. In soil set testing, you go for sampling and then processing of the sample. Then first you extract the nutrients from the soil, and then after extraction, you do chemical analysis. And after chemical analysis, you do the interpretation of the result, whether your nutrients are sufficient or insufficient in the soil, whether they fall in very low, medium, high, or very high categories. Now we have 5 categories. So according to that, we can rate our soils, whether a particular nutrient is medium, high, or low. Very low, low, and medium are considered as insufficient, and high and very high is considered as sufficient. The fourth approach of evaluation of soil fertility is by microbiological methods, and all these microbiological methods are obsolete now. Nobody is using them to evaluate fertility. ये पुरानी किताबों में लिखा रहता तो हम इसको पढ़ाते रहते, otherwise they do not have any significance. इनका क्विज में जबरदस्ती लोग क्वेश्चन पूछ लेते हैं कि एजोटोबैक्टर प्लेग टेक्निक यूज्ड टू नो द स्टेटस ऑफ फास्फोरस, पोटेशियम. मुझे पता नहीं है, भूल रहा हूं मैं, बट they are used to see the status of nutrients in soil. Aspergillus niger, Cunning, Gamela, Lake method, carbon dioxide evolution method. This is good. This carbon dioxide evolution methods, this tell us mainly activity of the microbes in the soil. If you get more CO2 evolution, that means your microbial activity is more in the soil. The remote sensing method is also used, which is called as normalized difference vegetation index for certain nutrient, mainly for nitrogen. You can use this remote sensing, but it is indirect method of evaluating soil fertility. And then the best approach is to go for field experiment. These are the best way to conduct the field experiment under different fertility levels and find out the optimum level of fertilizer. So at the end, field experiments are the best judge for evaluation of soil fertility, because in these experiments, you will have a control treatment that can tell us that how much nutrients can be supplied from the soil. So now steps in the interpretation of the results by conducting. So in the last slide, you have seen that conduct of fertilizer experiment is the best way. So we will continue this in the next link. I think it is less than a minute now. So we go to the second link and we start from here. Okay, you can click on the second link sent to you today. So welcome back. As I have told you that the best way to evaluate fertility or best way to decide the optimum dose of fertilizer or decide the right quantity of fertilizer that gives us maximum profit is by conducting the field experiment or agronomic experiment, we call it. And based upon these field experiments, we can develop some regression equations, regression lines, and we call it actually soil test crop response. Soil test crop response. So that approach is the best to give recommendations of the nutrients. And these regression equations can be developed for different regions, different soils, different climates, and they can be used by soil testing labs to give recommendations of the nutrients. So therefore, fertilizer experiments are important. So first of all, what we need to do, we need to conduct fertilizer experiments or fertilizer experiment under field condition. Because pot condition is also not good. You can do pot experiments on fertilizers, but they are not really representing the field conditions. In field conditions, nutrient movement is different. The temperatures may be different. The water movement may be different under field conditions. The soil depth may be different. The plant growth may be different than so they are not truly representative of the field condition. Therefore, we need to conduct the field experiments in place of pot experiments. When we conduct field experiment on fertilizer, we can have different doses of a fertilizer. We can evaluate one fertilizer at a time, or we can have two different fertilizers like N and P also. Sometimes we can even have three fertilizers in factorial experiments. It depends upon nature of experiment, but you can have one variable, two variable, three or four, as you wish. If you take only one variable at a time, then that is simple fertilizer experiment. If you take two factor, two variable of fertilizer or more, then it becomes complex fertilizer experiment. So for complex fertilizer experiment, you can have sources also. Fertilizer means, suppose it is nitrogenous fertilizer, but you have two sources. One could be urea, other could be urea ammonium nitrate, or other could be ammonium sulfate. Or you can compare two sources or three sources of fertilizer applying the same quantity of nitrogen. So three sources can be compared. Which source will give us more benefit? So this can be easily done here. Similarly, for sulfur also, you have 2-3 sources of sulfur. One could be gypsum, other could be bentonite sulfur, and third one could be other grade of sulfur. So these three sources of sulfur can be compared at different levels of sulfur. You apply, say, 0, 20, 40, 60, 80 levels of sulfur through three different sources. So you can have three different lines for each source. So that way, another interesting point is that you can have, for example, nitrogen levels, only nitrogen levels, but you can test it at 5 varieties of rice or 5 varieties of wheat or any crop. So it can be done. You can take varieties as variable and also levels of fertilizer as variable. So in one experiment, I can know the response of 5 different varieties. So I can give recommendation which variety would need what level of fertilizer would be ideal for which variety. It can be done by conducting fertilizer experiment. We are doing it. You are doing it. You may know it. We are doing it. Many times in our experiment, we take levels of nutrients and different varieties. So we can see performance of different varieties under different levels. Suppose it is 90 level. So at 90 level, which variety is giving less yield, which variety is giving more yield. And then at 120 also, we can see some varietal differences. So if there are 5 varieties, so you can have 5 different lines for 5 varieties. I will teach you how to do it. Don't worry about it. I'm just advertising what to make more interesting. Now you have conducted fertilizer experiment and then you have obtained the results. Results in terms of yield, mainly with respect to yield or maybe growth, whatever is your objective. Depending upon objective, you can record the yield. Maybe in some cases in potato, it may be tuber yield. In fodder case of fodder, it may be fodder yield. Whatever economic part you have, you can record that data. And then very simple is ANOVA, analysis of variance. You might be knowing that you record the data for yield and you know how much fertilizers or levels were there. And then you can do statistical analysis. You have data in your hand and then you can go for ANOVA analysis. Then after ANOVA, analysis of variance means F-test. You must be taught about the randomized block design, factorial experiments, split plot design, etc., etc. Did they teach you?
Sir, it will come in next semester, sir. There is a course of statistical design, so in second sem.
Okay. So in this case, first, what is required? You need to tabulate the data. Treatment-wise, in the first column, you will have treatment, say 0, 30, 60, 90, 120, whatever level you have in the first column. In the second column, you will have yield data. Yield data for replication 1, for replication 2, and for replication 3. Okay, so you have 3 replications, and then you need to work out certain sum of squares. Sum of square, first of all, you will be doing grand total, and from that grand total, you need to calculate corrected sum of square, and then you need to calculate sum of square for this treatment, sum of square for replication, sum of square for error, and so on. This can be done manually. You will be taught how to do it. In RBD, suppose RBD is simplest design. So you have done this analysis, and ANOVA means analysis of variance. So in yield you will find variation. In control treatment, you will get less yield. In 30, the yield will increase. In 60, 90. So you will get variable yield. So variable yield, now you need to look for the reason why this variation has happened in the yield. For this, you should break down this variation into different sources. So first source of variation is replication in ANOVA, and second source of variation could be treatment or nitrogen level. And remaining unexplained variation will be your error. And there may be some total of all these will be total variability in the data. That is called as total sum of square. Total sum of square. So this will be taught to you. And then treatment these sum of squares are divided by degrees of freedom. Yeah, for example, you have 3 replication. Degree of freedom is 2. For treatment, suppose 5 nitrogen treatment, so degree of freedom will be 4. And then you multiply these two. This will be your error degree of freedom and make the total. So this is how these error degree of this respective degree of freedom, if you divide sum of square, you will get mean squares. Mean square due to treatment, mean square due to error, etc. And then mean square treatment divided by mean square error, you get F calculated. This is called as F test or Fisher test. So in this case, if your calculated values are greater than the table value here in F test, you have 2 degrees of freedom. One for the treatment, other for the error. Suppose for treatment, degree of freedom was 5. For error, it was say 6. So at 5 and 6 degree of freedom, here you have 2 values, N1 and N2, at which you see at 5% level, you can check. You must have seen F table. In F table, there are 2 degrees of freedom, one on horizontal side, other on vertical side. So suppose it is 5, 6. So 5, you need to see horizontally, and then 6 degree of freedom vertically at the prescribed level of significance. And you need to check at 5%. So what is the value, F table value at 5% level of significance and at 5 and 6 degrees of freedom? So you will know it. And then compare the calculated value with the table value. If your calculated value is greater than table value, then your results are significant. Means this variation is genuine. This variation is genuine and not due to some chance factor. So this is how we do the F test. F test significant means your treatment differences are significant at prescribed level of significance. So now you need to go for a statistical analysis. You need to see whether F test is significant or not. If it is significant, if results are significant, then we can do correlation and regression analysis. Then we can find out the optimum dose of the fertilizer. Otherwise, if our results are non-significant, we need not to go any further. We stop here and it is all over. There is no fun in doing further analysis. Okay. So if results are significant, assume, then we can do correlation and regression analysis. With the help of correlation and regression analysis, we can fit the response curve. And this response curve of relationship of input and output or relation of fertilizer and yield can be used to determine the optimum dose of fertilizer. It can also be used to predict the yield at unknown level of X. At unknown level of X, we can make predictions from that equation. So that is the purpose of developing regression equation, regression line, regression model, regression curve, whatever you call, they are same. So this is called as response curve. You can call it response curve also, response equation. They are similar things. So we need to go for response curve fitting, and then once we have found out the response curve, then we can apply certain economic principles. Some economic principles I will explain you later, and we can find out the optimum dose of fertilizer. If relationship is linear, you cannot find the optimum dose of fertilizer, but from quadratic regression equations, we can work out the optimum level of fertilizer or any other input, which is having numerical values in increasing orders. So here in this subject, what you see is agronomy is there. You know, you have to record the data, conduct the field experiment. Then you need to do statistical analysis. So statistics is there. And finally, you need to put some economics in perspective. Therefore, 3 subjects are combined together in this particular subject. Yeah, Palash, you want to ask?
No, sir.
Nothing? Okay. Now, it is better to know in detail what is response curve now. I have told you that response curve will be used to predict, make predictions, and also to find out the optimum dose of fertilizer. So let us know in detail what is response curve, what is response curve fitting, etc., etc. And to understand response curve better, we should also have idea of correlation and regression. So I'll touch upon all these subjects so that you will have very clear understanding of this subject. There should not be any confusion. If you come across any confusion, any doubt, stop me. At that particular moment, I will answer it. Don't keep questions just roaming in your mind. Just ask them, put them out. So response curve is functional relationship between input and output. It will be a response equation. Okay, function is equal to equation. ऐसे भी कह सकते. Equation can be represented in a graphical form. Then it will become a response equation can be converted into graphical form, which will be called as response curve. Means just relation of X and Y. Relationship between yield and fertilizer rate is fertilizer yield function or fertilizer yield response curve with a general mathematical form. Model भी कह दो, इससे डरने की जरूरत नहीं, कुछ भी बोल दो. Model estimated from experimental data will give a realistic mathematical representation of the biological relationship indicated by the data. So such kind of equations are very potent, very effective. They can represent the relation of or biological relationship between data or between your independent and dependent variable. Now there are different types of response curves. Response curves means relation of x and y. You can see. So first degree, this is degree or power of the variable, which is x here. So first degree is linear, and equation will be called as a straight line. Equation will be a straight line when you have first degree, means x power 1. When you have x power 2, it is called second degree quadratic equation, and the curve will be called as a parabola. Then third degree is cubic parabola is the curve. Fourth degree is quadratic. It is quartic. It is not quadratic. You can correct it. It is quartic. Q-U-A-R-T-I-C. Quartic. Quadratic is 2. Q-U-A-R-T-I-C. Quartic. It will be quartic parabola. And then fifth is quintic and quintic parabola. Don't bother about this. We need to see only the first, second, and third one. Cubic. Cubic means x power 3. So, and then you also see what is production function. So production, you can call it production function or response function. Production function is somewhat bigger thing, and response function is a smaller thing. So a production functions or response function is a mathematical expression that describes the physical relationship between input and output. The relation is expressed as y is function of several inputs, x1, x2, x3, and so on. So this is simple response function or response equation. Now you see different forms of response curves, how they look. So it is quite interesting. See, if it is linear is a straight line. It is a straight line. It can go upside also. It is falling in this side. It is negative relation. So here you see there is no any peak. It is a straight line. There is no any curve. Now you see this quadratic equation. In quadratic equation, you have two powers. So therefore, you have one peak. Here, only one peak is there in the line. So therefore, it is quadratic. In cubic, power is 3, x power 3. Then you have two peaks. One is here and other is here. One this side, other that side. So this is cubic. Now you can see quartic, and one more equation is there, which is exponential. Exponential equation, you know, exponential e power x or something like that. Those equations are exponential equations, and regression is exponential regression. Actually, there are two kinds of equations. One is polynomial equation, other is exponential equation. In algebra, there are basically two kinds of equations. Equations means relations between different variables. One is polynomial, other is exponential. In polynomial equations, the power of the variable is a numerical number. In exponential equation, variable itself is the power. For example, if I say e power x, this is exponential equation. If I say x power 2, x power 3 in an equation, then it is polynomial equation. So now you can see exponential equation, the exponent means power, or part of it is a variable, maybe part of it. For example, 3 power x or is equal to 81. This is one equation. 5x minus 3 is equal to 625 or e power x. So such equations are exponential equation, where you see x is there in the power. A polynomial equation is an expression consisting of variables, coefficients, and exponents 1 and 2. A polynomial function is one which has a single independent variable. So you have polynomial equation. You must have solved in algebra. Algebra, y is equal to a plus bx, y is equal to 3a plus 2a minus 36, something like that. वो solve करते थे equation. So you can see y is equal to a plus bx plus cx square. This is polynomial equation with degree 2. Maximum degree is 2. Therefore, it is called as quadratic equation. Y is dependent variable. Dependent variable means the outcome of variable is dependent upon other variable. X will decide the value of y. Therefore, it is a dependent variable, and other, which is really the causing variable. Causing variable is independent variable, and the effect is your dependent variable. किसको इफेक्ट कर रहा, किसको अफेक्ट कर रहा, वो आपका डिपेंडेंट हो गया, और जो अफेक्ट डाल रहा है, इफेक्ट डाल रहा है, that is your independent variable. So x is independent variable with degree 1 and 2, and highest degree is 2, thus a binomial or quadratic equation. So exponents in a polynomial equation can only be positive integers, natural numbers, 1, 2, 3, 4. Negative integer exponent is never a part of polynomial equation. You will never have negative power of variable x. The independent variable can occur multiple times. A plus bx plus cx square plus dx cube. Different x's are separated by addition, subtraction, or multiplication. The degree of polynomial is highest degree of the exponent that exists in the equation. Now, polynomial of degree 0, if x power 0, then there is no relationship where there is no regression variable. Here there is no x, so in 0 there is no relationship. Polynomial of degree 1 is a linear or a straight line. Equation is y plus bx. Polynomial of degree 2 for quadratic type equations, y is equal to a plus b, bx plus cx square. You should remember that in the equation, all values are in plus. All values are in plus. If I ask you equation, then you will say that all the values are in positive. But when we actually fit this equation, then there is a fall in the curve. Fall in the curve, therefore value of c may become negative. But equation as such has all the positive values. Polynomial of degree 3 for cubic type of curved relation, y is equal to a plus bx plus cx square plus dx cube. This is quadratic equation. Then polynomial of nth degree. So y is equal to b0. In place of a, b, c, d, you can also use b0, b1, b2, b3, and so on. Is it okay, Palash?
Yes, sir.
Now, types of equations or types of curves. Heading is types of equation and types of curves. So polynomial of degree 1 is a linear. Response is a straight line. Polynomial of degree 2, 3, 4, 5, and n are curvilinear. The first is linear, other are called as curvilinear or non-linear. Quadratic, cubic, and higher are curvilinear or non-linear, representing different versions of the law of diminishing return. Okay, I already told you. Economic interpretations are made from these functions. Procedure for fitting different response functions to experimental data are available. How to fit these equations? Fitting these equations means how you can develop the equation or how numerically you can find out the equation. Such methods are available. And those methods are basically method of least square. Method of least square is used to develop or to find out the relationship between independent variables and dependent variables. Procedures for applying economic principles to experimental data via different response functions generally worked out by the individual. So procedures are available to apply economics to the response curves to find out the optimum level of inputs. Those procedures I will explain you later. The linear response implies constant return. This suggests constant returns. Application of economic principle to this function is different from and simpler than the application to curvilinear diminishing return function. So problem here is that you cannot decide the optimum level of the input in this case because the return is same for each additional unit of variable. So therefore, here you cannot decide. Now, I just seek your more attention how to fit the response curve. Okay. So this is a field experiment data. Experiment was conducted by using different doses of fertilizer, any fertilizer. Say starting from 0, you got 30, 60, 90, 120, 150, 180, and up to 208 and 240. So there are several levels of fertilizer. And you see, this is the yield recorded. Maybe any unit, it does not matter. And these are relative yields at different units of fertilizer, levels of fertilizer. And now you have plotted the data. This blue, 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 this is original data. Original data. So original data, you know, we have conducted the field experiment. And at first, we have done the F test. F test was found out to be significant. And then if it is significant, then we can develop the relation